This is the homework help video for Physics Homework 4.1. I will do 1, 3, and 5. Let's go ahead and look at number 1 here. We've got Katrina the ballet dancer, and she has a mass of 45.0 kilograms. And to start off, we want to know her weight on Earth. Remember here that weight is just equal to the force of gravity. So we're really looking for a force of gravity here. So to find that, we're going to use F equals ma. So force of gravity equals mass times acceleration, which is going to give us 45.0 kilograms. And we know that the acceleration due to gravity is 10 meters per second squared on Earth. And so the force due to gravity, or the weight of Katrina, is 450 newtons are your units here. That's your answer to part A. For part B, we have to change things a little bit. We have a different acceleration now because she's on Jupiter. But what we're looking for here is her mass. So her mass really does not change. Her mass would be the same no matter where she goes. So her mass equals 45.0 kilograms even on Jupiter. It doesn't matter where she goes in the solar system, in the universe, etc. Her mass is always going to be 45 kilograms. Her weight, however, on Jupiter would be different because we're still looking at force of gravity there. So we'd take 45.0 kilograms times the acceleration, which is now 25 meters per second squared. And that's going to give us 1,125 newtons, 2.5 times her weight on Earth. So her weight would change significantly. Her mass, and this is for part B, her mass would not. Moving along to number 3 here, we've got Jake, a 72 kilogram lineman on Remington High School's football team, collides with Butch, a stationary tackle, and is brought to a stop with an acceleration of negative 20 meters per second squared. What force does Butch exert on Jake? We know Jake's mass, which is 72.0 kilograms. We know his acceleration, which is negative 20.0 meters per second squared. And we're looking here for the force exerted on Jake. So we'll put force of Butch on Jake equals that, and the force of Jake on Butch is the next one that we'll do. So first off, the force of Butch on Jake. We know that Jake's mass is 72 and his acceleration is negative 20, so all we have to do is multiply those two things together. So we'll take force equals mass times acceleration, so equals 72 kilograms times, negative 20 meters per second squared. And we should get there negative 1,140 newtons for the force, and this is the force of Butch on Jake. So this is your answer to part A. For the second piece, there's a little bit of background knowledge that we have to have here. This is an action-reaction. This is kind of a Newton's third law question. So when we ask what the force of Jake on Butch is, what force does Jake exert on Butch? It's going to be the exact same magnitude in the opposite direction. So the force of Jake on Butch equals 1,140 newtons. Notice that it's the same magnitude, but in this one we have the negative, and this one we are positive. Same force, opposite directions. Remember that Butch can't hit Jake without Jake hitting Butch. So that should be your answer for number 3. Now we'll move on to number 5. And on number 5, we have William Tell, and he's shooting a 30-gram arrow. We'll just write down everything we know. 30.0 grams. Through an 8 centimeter thick apple. and we'll just say 8 centimeters equals delta dx, I suppose. Sitting on top of his son's head. If the arrow enters the apple at 30 meters per second, so VIX equals 30.0 meters per second, and emerges at 25 meters per second in the same direction, important, so VFX equals 25 meters per second. The question here is with what force has the apple resisted the arrow? So we want to know how much force the apple exerted on the arrow. Now, to do this, we know mass, which is great, but to use F equals ma, we have to know the acceleration, and we don't know that yet. You'll notice the hint here that says you'll need to use a note card equation to help you find the acceleration. So this is a little bit of a different type of problem here. We're mixing a couple of different units together. To do this, we're going to use the equation VF squared, and I'm going to add the x's in here, VF squared equals VI squared plus 2A delta D. Now, I know I told you that little fib earlier about how these equations are only used for stuff in the y direction. That was because we hadn't done acceleration in the x direction yet. Now that we're doing acceleration horizontally, we can use these horizontally as well. So let's plug in here what we know. We know that the final velocity here is 25 meters per second. So we'll have 25.0 meters per second, and we'll square that, equals 30 meters per second was our initial velocity, and squared, plus 2 times our acceleration, which we don't know, but we do know the distance. We know that it's an 8 centimeter apple, so that's the distance that force was applied over. We do need to convert that to meters, so it'll be 0.08 meters. So 0.08 meters there. Now, let's go ahead and run through these calculations. We'll take 25 squared is 625 meters squared per second squared equals 30 squared, which is 900 meters squared per second squared, plus 2a times 0.08 meters. Okay, now our best option is going to be to subtract this 900 meters squared per second squared from both sides. Then that should give us negative 275 meters squared per second squared here equals 2a times 0.08 meters. Now I'm going to divide everything by 2 times 0.08 meters. And when we do that, we should get our answer. So divide by 2 times 0.08, and I get negative 1,718.75 meters per second squared, which seems awfully huge, but is actually correct here. So that's our acceleration. So now that we know our acceleration, even though it's awfully huge, it is correct. Now that we know our acceleration, we can plug that into F equals ma. So let's go ahead and do that, and I'm going to change colors here, and I'm kind of running out of space, so bear with me. We'll look at force here equals our mass, which if we go back up was 30 grams, equals 30.0 grams, which should hopefully give you a red flag. We can't do this with grams, we have to do it with kilograms. So we're going to erase this really quick. To convert that to kilograms, it's just going to be 0.30 kilograms times then, sorry, excuse me, it should be 0.03, my bad, 0.030 kilograms times then our acceleration, which we said was negative 18.75 meters squared per second squared. And I apologize about running into stuff. I am running out of space. And then our force here, finally, of the apple on the arrow should be negative 51.6 newtons. That should be your force there. Sorry about the mess there. I apologize. I was trying to fit this all in before I ran out of space. But there is your answer, and I hope this helped.